Welcome to One Grounds Management and the Basic Principles of Snow and Ice Science Training. This is continued training developed by One for its employees and service partners. This is the third training module in a series of modules developed to provide protection for our clients and ensure we bring as efficient as possible on our sites in providing snow and ice control services. One has recognized that there is a bit of a gap in the industry with regard to this education, and we hope that this will help promote professionalism in the industry and help improve your services as it has ours. To begin this training, it is important to understand the combined approach of snow and ice management. The two major categories of snow and ice management include mechanical and chemical tools and operations. The mechanical tools include things such as plows and pushers, shovels and loaders, trucks, and our labor. The chemical tools include chemicals such as sodium chloride, magnesium chloride, calcium chloride, and other de-icing chemicals. It includes labor, spreaders, and sprayers to further manage the surfaces and enhance our mechanical operations in achieving safe and accessible properties. The goal of any snow and ice management program is to achieve the level of service desired by the client. The complete snow and ice management program utilizes all forms of snow and ice control at appropriate times and conditions to achieve the client level of service. One Grounds Management has worked in the Northwest across multiple states for many years now. Throughout this time, we have recognized a need to increase in our knowledge and experience in professional snow and ice management, and also that of the service providers that have partnered with us. The chemical management of snow and ice has been, and we feel it continues to be, one of the most misunderstood functions in our snow manager's toolbox. Because of the advancement in science, technology, equipment, and other factors that influence our industry, we have determined that ice and chemical science training is the most significant need right now. This module will focus on the science of water cycles, properties of de-icers, and how to use them to further enhance the mechanical efforts and increase the safety and efficiency on properties. Throughout this module, we will discuss the properties of snow, ice, and de-icing chemicals and how they relate by examining the winter water cycle, conditions that affect that cycle, ambient temperature, surface temperature, and the molecular structure of water. We will also discuss the typical molecular structure of de-icing chemicals, their properties, the effects these de-icers have on winter water, and strategies for using these properties to gain an advantage in managing winter water. Okay, now before we discuss properties of de-icing chemicals, there are a few terms that we need to know. First, de-icer is a common material used to melt ice, also referred to as ice melt. It does not really melt ice, but it decreases the temperature at which the water and de-icer chemical together become solid. Liquid is a de-icing chemical in liquid form. It is the shortened form of the term liquid de-icer. Salt brine is water that has been saturated or strongly impregnated with salt. The most efficient brine is formulated at 23.3% salt. Above 23.3% salt, it is saturated. Below, it's basically less effective. Effective temperature is the lowest temperature at which it is cost-effective or practical to use a de-icer. Sodium chloride works to -6 degrees Fahrenheit, but it would take a considerable amount of material and time for it to work. The lowest effective temperature with regard to material quantity and time for sodium chloride is about 15 degrees Fahrenheit. Let's start off talking about ambient versus surface temperature. Ambient temperature is often mistakenly used as the measurement by which snow and ice control activities are determined. The standard household freezer has a default temperature setting of about 0 degrees Fahrenheit. This is essentially the ambient temperature of the freezer. How long does it take for a tray of water to be frozen into ice cubes? For cakes, how long does it take to bake them in an oven with an ambient temperature of 350 degrees. Both processes involve energy by either removing it from the water or applying it in the oven or the cake batter. It would take 6 hours for ice cubes to form and reach the same temperature of the freezer. The cake would take about 45 minutes to bake. Ambient temperature is a long-term process for removing or applying energy to affect the state of a material. Surface temperature has an immediate effect on materials that come in contact with it. Have you ever spilled a little bit of the cake batter in the oven? It cooks immediately. Water spilled in the freezer freezes quickly or immediately as well. If surface temperature did not have such an immediate effect, the tongue on a frozen pole wouldn't be that funny. Now that we have established that surface temperature is key in determining management approaches, it is time to discuss the basic structure of water and the different phases of water in the water cycle when energy is either removed or applied. In water below 32 degrees Fahrenheit, the bonds between hydrogen and oxygen molecules become very strong and rigid and conform to a structure that expands and becomes solid. The hydrogen bond between them is what is influenced by the application or removal of energy. Above 32 degrees Fahrenheit, the hydrogen bond is weakened and they are able to flow around each other in a more fluid arrangement. As continued energy is applied to the water molecules, they absorb the energy and break out from the other molecules into vapor. As energy is removed from the water molecules, whether in the gas or liquid state, the attraction to other water molecules is increased and the process is then reversed. Now that we understand the water cycle and the removal and application of energy to water and what happens, let's look at some of the chemicals themselves. This image shows the structure of sodium chloride. It's a cube-like shape and it's typical of most of the granular chloride-based de-icing chemicals. When sodium chloride is introduced to water molecules, the bonds between the sodium and the chloride weakens and they are attracted to the water molecules. This mixing will occur until there is no more water molecules to bond with. This occurs at 23.3% sodium chloride to 76.7% water ratio. The mixture will remain in this liquid state as long as energy is neither applied or removed from it. If the sodium chloride solution has energy removed from it, meaning we cool it below its working temperature, the hydrogen bonds between water molecules is strengthened, and they bond with one another again despite the sodium chloride molecules, and again form the solid rigid structure of ice. To sum this all up, common de-icers keep the water in liquid form at temperatures down to their lowest working temperature. If the temperature decreases beyond the working temperature, freezing will occur. If water is added to the solution, any water molecules not bonded with de-icer will freeze, even above the working temperature. There is another reaction between water and de-icers that we must consider. As the temperature of water in the solid state decreases, the amount of de-icer needed to melt that ice increases. This is why we need to understand what the surface temperature is. It is a factor when calculating the amount of de-icer needed to keep a surface safe. Our next training module will show the new additions we have made to our phone app that will calculate these amounts for us, given the surface temperature and the surface area to be treated. In the chart to the right, you can see that 1 pound of salt will melt 46.3 pounds of ice at 30 degrees Fahrenheit. At 20 degrees Fahrenheit, 1 pound of salt only melts 8.6 pounds of ice. It is vitally important that we know what the surface temperatures are in order to properly calculate the needed material on sites. Now that we understand how de-icing chemicals react with water molecules, we need to discuss another property of de-icing chemicals that influences water in the form of ice and liquids. The specific gravity of de-icer chemicals is higher than that of water. In other words, if you have a 23.3% solution of brine, it is 23.3% sodium chloride. The sodium chloride will add weight to the liquid. For two containers with the equivalent volume of salt brine in one and water in the other, the sodium chloride salt brine will be heavier. As we evaluate the difference between sodium chloride and magnesium chloride, the magnesium chloride solution has a higher specific gravity than that of sodium. Also, calcium has a higher specific gravity than that of magnesium. All of this is important because it helps us to understand how the materials will work together when applied to surfaces. Now that we have discussed the main properties of these de-icer chemicals and the molecular structure of water, let's show how they react with each other and focus on the principles to apply when determining a course of action with regard to snow and ice management. First, because the de-icer chemicals are heavier than water, they will work their way to the bottom of the container or will settle on the surface where they are applied. Second, the three most common de-icers have differing effective temperatures. Thus, knowing the surface temperature you need to control will help you determine the most appropriate material to use to achieve efficient results. Finally, water vapor is made up of only water molecules. De-icer molecules do not evaporate, but get left behind on the surface. In fact, the way salt is mined is by flooding an area with salt water, then allowing the water to evaporate and then collect the salt that was left behind. Now let's apply these principles to what we do. Remember we discussed the water cycle earlier? This is the application of the water cycle to an impervious surface. It is important to note that most snow events happen at an ambient temperature of about 28 degrees Fahrenheit. However, the surface temperature may be higher than that. That is why sometimes snow does not stick to the surface. But as the surface cools to meet the ambient temperature, the water freezes and bonds to that surface. If the surface is warmer than 32 degrees Fahrenheit, increased precipitation causes increased runoff. When the surface or ambient temperature is above 32 degrees Fahrenheit and warm, evaporation occurs and residue is left behind on the surface. Okay, so now let's consider the application of de-icers to the impervious surface and what should occur during a storm event with, say, 6 inches of snow projected. Knowing there will be low temperatures and accumulation of snow, we should perform an anti-icing service on the property. This will allow us to prevent or minimize the bond of snow and ice to the surface. We do not anti-ice to prevent the accumulation of snow, but rather to make the mechanical efforts of snow removal with plows, pushers, and shovels more effective. Anti-icing also does not require the same amount of material as a de-icing application. A good rule of thumb is about a third of what would normally be applied. However, there is specific site conditions to consider when applying, and these should be determined when performing the service. Now that we have performed the anti-icing service, we wait to see what happens. As the storm progresses, there will be some accumulation on the surface once the de-icer that was applied goes into solution with that initial precipitation. Remember, we did not apply a normal de-icing service, but an anti-icing service. The goal was to prevent the bond of ice and snow to the surface. It is now time to use mechanical snow removal services to keep our property safe and accessible. The de-icer is still working, and we can perform a couple of more mechanical snow removal services without needing to reapply de-icer. Notice that there is still some de-icer residue left behind on the surface. Because the de-icing chemical is heavier than water, it stays at the surface, and our mechanical services removes only the snow and ice above it. Once we have performed our final mechanical service and no more accumulation of snow is expected, we need to perform a de-icing service. Throughout the storm, we have had loss of our de-icer, and there is some dilution of this de-icer chemical on the surface. The final application of the de-icer will ensure any moisture on the surface will not freeze and cause unsafe conditions. Okay, to recap our training then, there are a few major properties and principles that need to be considered when determining your snow removal and ice control activities. First, for every degree below 32 degrees Fahrenheit, the amount of de-icer needed to keep water in a liquid state increases. Remember the chart that was shown for sodium chloride and the amount of ice 1 pound of de-icer would melt given various temperatures. Secondly, precipitation above 32 degrees is usually in the form of rain. Material should be applied judiciously because it can become diluted. During heavy rain or freezing rain, it is not recommended to apply ice melt. Finally, evaporation will leave de-icer residue on the surface. This helps maintain safe conditions in the absence of excessive runoff or dilution. The de-icer residue continues to work before a new application is needed. Inspect the surfaces and apply as needed. Remembering these principles can help you use de-icer materials more fully to enhance your mechanical snow removal efforts while saving material costs for you and your client. One has invested considerably in developing its own in-house training and invested with consultants and industry organizations to help promote professionalism in the snow and ice control industry. Delkeep has been an invaluable resource for one in being able to improve its own processes and knowledge. He has developed a training course that has significant amount of information that would be beneficial to most companies. He is able to help you in ice science training, engineering brine making systems, on-site snow and ice control service optimization, equipment calibration, and quality control systems in your ice melt and brine materials. He offers certificated education that can help you meet continued education hours and most of all, help you provide professional services to your clients. One is a member of both the Accredited Snow Contractors Association and the Snow and Ice Management Association. Both these organizations are working to increase the professionalism in the industry and show the need of quality services for clients. Information was utilized from both to develop our training modules this winter. There are many benefits these organizations have for snow and ice contractors and professionals. Okay, finally, there are other organizations that information was gathered from to produce this training, and other organizations that have influenced one in its goal to become more professional in the industry, increase our knowledge, and become a premium snow removal and ice control provider in the Northwest. Would like to thank them. A couple of them I'd like to point out is the John Allen Consulting firm and also the Snow Fighters Institute. One Grounds Management has utilized John Allen Consulting in achieving our ISO status, and we've also had individuals go to the Snow Fighters Institute to learn and improve our administrative and business practices. So I'd like to say thank you to all of them. And then finally, if you have any questions about this, please feel free to contact us. This training has been developed specifically to help our service partners to increase their knowledge and become more professional. We thank you for all the hard work that you guys do and the good work that you do and the opportunity to work with all of you in the different areas. We look forward to a great year this year. Now let's go get them.